So what are we going to cover? We're going to cover vibration design, not natural frequencies, not earthquakes. Vibration design in floors and staircases. That's it. So we're going to be basing it all on the SCI publication P354. Quite a mammoth read, quite technical in places, quite informative. There is also a Concrete Society publication 016 for concrete floors, but in this case we're going to do a composite floor, and we're going to look at the natural frequencies and mass participation, and then we'll look at floor vibrations and these things called response factors. We'll look at staircases as well, and then the response on a floor from a staircase. And then we'll get into things like a vibration dose values, resonant build-up, and steady state versus transient. So that's what we're going to cover. Okay, so let's get my MasterSeries up. Here we go, MasterSeries 2019 from the 24th of July. So let's look at our frame that we're going to look at. Obviously we don't want to waste time generating the frame. So it's a composite floor with columns and beams and a slab. It's got some openings and it's also got a staircase. Very straightforward. And if I was to put this into 3D solid, we'll see that it is a solid slab with steel beams underneath. And whoops. And then we can zoom in and see plate sections and box sections for our staircase. First thing to note is that while it's a composite floor, we have analysed it as a finite element slab, and that is as recommended in the P354. The second thing we will note when we turn off the 3D, for those who are familiar with our software, is that it is not pinned. Because our vibration analysis is at quite low stresses on the structure, and we're talking about footfall analysis, people walking past a corridor causing effect, or people finding they're walking or dancing and it's too springy. This is not loading the structure up that much. So the document also recommends that you do a fixed rigid analysis, because the concrete is rigid at those levels. The next thing we want to think about is the floor, the columns themselves. Now the columns can either be full length and fixed at the ends, or half length and pinned. I've gone for half length and pinned just to make my life a wee bit easier. If we look at the supports, we will see that we've got pins in the bottom, but obviously at the top we've got them only restrained horizontally, so that they can go up and down if they need to move a wee bit with the vibration. At the floor level that we're considering, we've only put a couple of lateral restraints to simulate where we'd have bracing systems, shear walls or whatever on the structure. Again, very, very straightforward and simple. So we said it's a finite element surface, so let's go in and look at the structure. And you'll notice we're doing one floor, not a whole lot of floors, because it's very computationally hungry. So doing an isolated floor is the recommended methodology. So here we go. Here's our first composite, our finite element floor. I've split it into several different isolated FE surfaces because we are going to assume and consider the span of the ribbed deck. So let's look at our floor. There's our floor. There's a nice big opening. And we have then gone and asked for and we can apply a rib deck, but in our case we've already set it up as a multi-deck 80. And 80 ribs, 136 wide, spacing 300. Young's modulus The Young's modulus of concrete is your dynamic modulus of elasticity, which is higher than your normal concrete modulus of elasticity. So we're taking 38, and obviously we're taking gross section as well, so we're not reducing that by any material factors. Very straightforward. The slab is at 180 mil thick. That's nearly everything. We've looked at the material. Attached beams. We have attached all these beams as you would expect, and we have set them to be bottom connected. So it's the full depth of the beam, the full depth of the 457 plus the full depth of the concrete. So they are sitting on the bottoms. And that's again very straightforward. The other important thing is the direction of the span. If I put this in plan, you will see if I turn on my little diagram, my X is running in that direction. So when I go to my material, you will see that I set my rib axis to be 90 degrees, so the ribs are running in that direction, and that's as you would expect. That will get quite complicated when we get into these axes, so instead what we have done to make my life easier is come along, and on the main border I have set the two nodes that I want to be the axes nodes. So looking at this in 3D, zooming in, you will see very straightforward 16 to 18, the two nodes, and no adjustment. So that's my x-axis, and then I just say it is flush to the x-axis. When I look at my material, it is 0 to the x-axis. So each of these is set parallel to this outer surface, and that acts as a good averaged strip around the deck for these areas. And that's all very straightforward. Now, turn off the node numbers. The next thing we want to consider is the attached beams in these areas. And this is where it gets interesting, because we do not attach all of the members. We attach the first member here in this one, and when we move to the next surface, so that one's that one, we take that and that in this one, and we're taking the, whoops, going the wrong way, and again and again and again. So we're not duplicating our attached beams into two different surfaces. We attach them to the one surface, and that is again the more sensible way of doing it, and every time we are bottom connected. Loading, let's just go back to loading case 1, or sorry, surface 1, and look at the loading. The loading again is very straightforward. We've got our live load, 2.5 kilonewtons, and we have a superimposed dead load of 0.5 from surfaces and whatever, and nothing else. The self weight of the rib slab is handled automatically, so we don't have to worry about that at all. So that is my frame. Back out to here, just close down the FE surfaces. I'm happy, and I just come straight in to dynamic analysis. Going to save it, yes. Not certain why I wanted to save it. It's going to remesh it, yes. There it goes, creating its mesh. And the default mesh will be more than satisfactory here, unless we start to get some really weird answers. So off it's going, it's calculating its FE surfaces before it gets into the structure. So here we are, and we're going to look at our dynamic analysis. So first of all, we look at these natural frequencies, because it's the natural frequencies that we then use to apply our vibration design. So first of all, the big thing is loads. Our mass loads and our dead loads are factored by 1, because we take the full amount of those, but the dead loads by 0.1 or 10%. There are two schools of thought in the 354 publication. Initially it says 0.3, or 30%, and then it contradicts itself and says down to 0.1. 0.1 is a more conservative association and it's going to give you worse results. So 10% or 0.1 is the sensible answer here. Moving over to our self-weight, yes, we are going to include density, and we're going to include it in the D1 group, so that's all good and fine. We've gone for a 3D analysis because we have our columns and our staircase to consider. If it was just a plain frame with supports, then we could have gone for a 2D analysis, which would obviously reduce your solution. Frequencies. Now the frequencies we need to consider are quite a lot. We need to consider everything up to 8, and then we need to look at the fourth harmonic of that, so we're moving up to around 30. So if I say from 0, in here, to 30, or even 32 if you want to be more exact, but it's not an exact science, we can then consider that. And I am now going to ask it to process this, and I'm just going to go analyze. And this will take quite a wee bit of time. It's going to take a minute or two. We will notice that we're dealing with 17,000 degrees of freedom, and you can square that to get your solution on the system. Here we go. It's finished. So what have we got? We've got our natural frequencies, and if I can see for any natural frequency, and I can just increase the scale, you can see what's happening. So the first frequency is down here on the staircase, and then the next one is over here on the floor. But you can also see that the staircase one didn't really have any vertical mass participation, so that it's got absolutely minuscule, so it's not that significant. The mass participation of this one at around 8.7, 8.8 frequency is taking this a load. And we can see also that our global mass participation of around 70, 75 is very, very significant and shows us that we are in the realms of the correct results. So if we looked at this and asked it to run, it's going to show you how the structure is deflecting. And these aren't real deflections, they are, what's the word for it? Equalized. They're all brought back to down to a factor of 1. They're normalized with each other. So I can just stop that. And obviously if we went back down to a different frequency, we would see that running over here, but again with a far lower mass participation. This has got a 16%, 13% mass participation, so this might be more significant. That's taking in this area here, which is quite interesting. So that is the natural frequencies, and I'll just stop that. What we now want to run is our vibration analysis, so into vibration design. So the first thing I'm going to do is add in a loading case, and I'm going to say that it is for residential. I'm going to put the dampening down to 1. It'll be 354 steady state, so we'll look at steady state and walking. We'll also go for the recommended for walking of 1.8 to 2.2, but we'll not take 100 steps. We'll speed things up by taking 10 steps. And we'll see here that we're getting our different harmonics on our base values. So for all these frequencies, we're going to look at everything. We're now going to say that we're going to go for multiple nodes. Put this in the front view, and I'm now going to say the response is equal to the loaded one. So we're going to look at the response at the same nodes and select all of the nodes in the floor. There we go. And then all selected, including these wee edge ones, and that's okay. So we're looking at the Y, and we'll just say go and do our vibration design. This is telling me that my response factor is coming up with values, and if you put this in plan, it can be quite hard sometimes to see when it's quite critical over here at 18. Now your response factor is set according to table 5.6 of the SCI guide, and again it can be quite vague. It's really talking about, and I'm just looking at page 5.6, and it's giving us values, and it's sort of saying, there we are, 5.6, offices multiplying factor, which is your response factor of around 4, residential 2, operating theatres down to 1. So we are seeing that our response is quite high. It is quite significant, and we would really need to go back and put in different thickness of material or different section sizes to try and get these response factors down. But we're going to keep going and look at what this can tell you, because this doesn't design, this just tells you what your values are, how close you are, how significant it is. And we can see that we're getting this as a factor of this. We can see that this mass participation is working here. So what we need to do next is to look at the most critical nodes. So it's listing these in order of the R factor, the response factor, and it's saying 18.1 is the most critical, and that is on node 1251. Make a note of that, 1251. So what we're going to do is we're going to create another loading case, and this time we're going to go for a single node, and again we're going to keep it that equals that, and it's going to be 1256. Was not correct, 1256, and you don't have a value there because they're equal to each other. We're going to choose our dampening as 1, and we're just going to run with that and see what we get. So vibration, and we'll now see that we're getting our value here at 2.2 hertz. Now we don't really need to go above 2.2 because that is what the code tells us, to 1.8 to 2.2. If I went up to 2.3 and reprocessed that, we'd see we are hitting this 2.20. Now that is in velocities. If I go for frequencies, it's at 12.38. So 12.38 is the value of response that we're getting there. So if we come all the way down here to the 2.2, we'll see we're getting 12.36. In fact, is the more accurate. Yeah, 12.36 is our response spectrum, exactly at the 2.2 hertz. So that's the second case we're looking at. We're looking at this area. So first of all, we looked at the whole floor with all the nodes loaded and all the nodes being sensitive. Here we looked at the one node and it being on its own, and it's all very straightforward to do. Now the next thing I want to look at is to come in and add in a third case, and we want to look now at our staircase. So in our staircase, we're going to just go for no weighting, dampening of 1, and it's going to be steady state staircase. And we're going to come down and we're going to select multiple nodes, response equals, and we're going to go and select for this loading case all of these nodes here. So what we're now getting back in here is these, and we're now going to move ahead, and because it's a floor we need to change our values, and we're going to go for 1.2 all the way up For a staircase, it's all the way up to 4.5. Now, 4.5 is one heck of a frequency, but if you can imagine two people running down the stairs out of, same weight, perfect timing, you could get up to double that normal value. We're going to run that all the way up on all the stairs. So let us go and see what we get from this. Oh, we need to close that and do the analysis on this staircase, and we'll see now that we've got values, but we can't see much in here because it's all pretty just a few lines. But if we turn on the 3D, we can see the coloration of the floor, and we can see here is the value that we're expecting. Now that's quite high. It's giving us 39 as our response factor. So what we would think about is staircases different to floors. So we'd probably turn around and think, well, we can allow up to 30, but really those loads don't occur for a long time, and they don't occur from somebody walking over a large distance. So what we're going to do is we're going to say, let's go for a vibration dose value. And we're going to say, let's go for 360 seconds. That is 6 minutes of excitation. And we're going to say that only one person comes down through here in any 6 minutes. So in this case, we'll just drop that to 1, or 1 pair of people. And we're now going to see what our values are. But if I just reanalyze for that, they've come down to 0.6. 0.6 is our dose values, and we're allowed, a low probability would be 0.2 to 0.4 from table 5.4 in the code. In this case, we're outside that range. We're up to a dose of 0.6. So 0.6 would be in the adverse possible, not low probability. So if you could accept, because this was very rarely used, you could accept possibly this higher dose value. But the next thing you want to do is to think about the fact that it's over a short distance. So we can say, let's go for a resonant build-up, and we're going to use it over a 5 meter length, not a 10 or 20 or 30 meter length. And if I now go and reanalyze for that value, we'll see the 0.56 has come down to 0.25. So for that short distance of excitation, we're into that 0.25 criteria. So that's fine. That's now working perfectly well, and we know that the staircase is fine when people are walking up and down it very occasionally. Now what I want to look at is, and I'm just going to add another case, I want to look at the effect on the floor due to the staircase being loaded. So let's put this back into plan view. Let's take off the 3D so we can see what we're doing. We're going to go for a steady state. We're still on the floor, so we are still going to consider it as a staircase, and again still going to consider it 1.2 all the way up to 4.5, and I'm going to reduce the number of steps down to 10 initially, and we're going to have a dampening again of 1. But what I'm going to use is not dynamic equals load, but I'm going to select the loads. So we have this area of staircase, people going up and down this staircase, and for whatever reason, this is a conference room, this is apart from a small corridor obviously, otherwise you'd be going straight into it, or this is an operating theatre or whatever, or very sensitive equipment. So I'm going to say OK, and then I'm going to select the nodes which I want to see what the influence is, and I'll just go outside there and just take this area of influence and just say OK. So we're now going to see what exciting these are will cause here. So we are going to say run that through, and we should get some nice pretty colors again in the floor slab rather than in the other. And we can see that we're into a response of 3.8. So if this was office, we're fine. But if it is something a bit more serious, we would need to do something to reduce this down. So that is very simply looking at the different approaches of steady state analysis. Now, there's also something called transient. And when you have transient loading, the loading doesn't have time to build up and build up. It's applied and goes away, applied and goes away. So we can also look at transient. And the assessment of whether you need to consider transient can be quite good fun. The publication 354 gives you all the guidance you need on whether or not to do it or not. But let's have a quick look. Adding in a fifth case. Not steady, but transient. And we're going to go for impulse. And we're going to go for these frequencies. But we're going to say the total time. Well, the total time is normally the inverse of your frequency. And if we're looking at frequencies between 1.8 and 2.2, we would say the average is 2. So let's look at a total time of 0.5. I'm going to look at a total time of 0.5. If I was to reduce that down to 1, it wouldn't, or 0.1, it'll be nothing because it'll be 5 little segments. I'm going to go for 0.1. I'm going to do it over 50 segments. And where are we going to consider? And what I want to do this time is to consider this area here and see what the transient loading on that is going to be like. So let's go and say multiple nodes and select the nodes, and we're going to go for all of those. I'll take it all the way out to there and apply. So that's my loading, and suddenly I'm going to come along and apply this here and go for a vibration design. So here we go, and we can see that we are only getting from the transient a little sensitive area around here of 7.8, which you could argue is probably okay. But if you were to say that you wanted to only really consider these areas, the main areas where people are sitting or doing things, nobody's going to be sitting right by the wall, then you're in that 4 area. So for an office area, it is perfectly good. So that's really everything that we wanted to cover. That's me having covered everything I wanted to cover. I'm going to look at some of the questions for you. Somebody's asking, from a certain organization, can we include Weststock beams? The model didn't have them, but if we'd put in a self-form beam, be it a plate girder or made up of roll sections cut and re-welded, yes, we could consider those. It will take the stiffness of those cellular beams into that analysis. Somebody's asking about this effect of the ribbed deck on the slab. Yes, the ribbing has a stronger strength, so you are going to span from here to here with the very deep and stiff component. But you have to remember that you also have the slab at the thinner surface spanning in this direction, and it will distribute some of the load accordingly. Now we could go back into our FE analysis, do an FE analysis on it, and see the dispersion of loading onto this as opposed to this from our shear loading on the two members. That would be an interesting exercise to look at. But the FE is always two-way, and it's this orthogonal ratio is set up due to the ribs automatically. No different to masonry in that respect. Okay, again, somebody was asking if is the 10% factor in the loading live or dead. Is the live. Always remember, it's the live loads that are the ones that may or may not be there. And when a room is full of people, you don't notice vibration unless, of course, they're all dancing. Somebody's asking about the natural frequencies. Natural frequencies is a whole different ball game to floors. If you were dealing with a piece of machinery jumping up and down, yes, you might be interested in your natural frequencies. But in reality, we're using something in here called Fourier series. So that's the transient one. Let's go back to the first one. We're using Fourier coefficients and Fourier series. So we're actually using a compounded set of vibrations all superimposed with each other to do this more realistic response factor. Because it's not the vibration, it's not the speed of the vibration that people get annoyed with, it's the acceleration. It's how fast they can detect it from the movement of their feet going up and down on the floor. It's not whether it's going up twice a minute or so twice a second or 4 times a second. It is how fast and how far it goes. So that's why it is a response factor, not to be confused with response spectrum, which is to do with earthquakes, and we're not covering that. It is acceleration, so it's actually the root mean square of it is the response factor, plus a few other things thrown in. Has the model been designed to work for static criteria? Well, this exercise is just to do with comfort in the building. It's to do with whether or not people are aware of vibrations from one area and the other. So it's all at serviceability limit state. You would have previously done a full design, not as an FE slab, but as a simple composite frame to design your beams and your columns and things like that in the structure. And of course those will be ultimate limit state, but not the vibration analysis, the dynamic analysis. So is this all one module? Very good question. What do we need? We need MasterFrame to create the model. We need the finite elements to create the FE mesh, and we need the dynamic analysis to create the vibrations and analyze it. So 3 models are required. In fact, even though this is a composite floor, you wouldn't even need the composite floor to do this analysis. You wouldn't need the steel design to do this analysis. In fact, you wouldn't even need area loading to do this analysis. So all you need is the MasterFrame with dynamic and vibration analysis together. Someone's asking, why did we limit the maximum frequencies to 30 Hertz? We limit it to 30 Hertz because we're way outside the 4th harmonic of frequencies that are important to stairs and walking, as set out in the SCI publication. How do we convert the results to loading case? It has nothing to do with loading cases. This is not a physical set of loads you have to design for. This is pure serviceability of your structure for comfort. Right, somebody's mentioning my transient case is actually got 5%, and if I noticed that, yeah. Oh no, it's 1%. Oh, it is 5%. You're absolutely right. So these are the values of 7.8. If I push this dampening down to 1, let's watch the birdie, see what happens. Of course, it's actually analyzing all 5 cases. So the more cases we put in, the more work it has to do. And this is coming from 7.8, and it can do it. And it's gone up with less dampening to 12.4. So yes, it is more significant. But we're still only getting that in significant areas. Our 8 value is significant, and it's only this area again that's really critical. So we may need to dampen it, but it depends on how you feel. And of course we could go for vibration dose and things like that to get things reduced even more. Does the mesh size help in your analysis? Yes and no in 2 ways. A coarser mesh is going to get us analyzing things a lot quicker, but may not be as accurate. I think you're really looking at dividing members into 1, 2, 3, 4, 5, 6 components roughly to get a mesh. So if I was to come out of this, and I'm going to come out now, I'm going to save the results. Yep. So if you look, it's identifying member lengths and saying, well, actually, we automatically need a higher mesh in here because these lengths of members are quite short. Whereas here it's happy to do quite a coarse mesh. Naturally, for any mesh, we could come into the FE surface mesh and go globally and change it down from the 1.5 meter global mesh, which is telling me that my things are at 3 meters apart. Yeah, so we're getting 2 each. So it's 3 meters and 3 meters and 3 meters, which is a traditional sort of example we use. But we could reduce that to 1 or 0.5. Bear in mind that everything is a square function, and if you reduce that to 0.75, you're going to get everything taking 4 times as long to work. Again, somebody's asking why we didn't pin them, we fixed them. Well, during your composite design for your ultimate state, they are pinned. But in these serviceability states for vibration, the stresses are actually quite low, and it's just feeling vibrations and things like that. You wouldn't think that somebody walking down a corridor would be putting any real stress on the whole structure. So in those cases, at those very low loadings and everything, the structure is working as a composite solid structure. And again, that is what the publication is giving us as a recommendation 354, SCIP 354. It's recommending that we do it rigid. Why would you need to undertake this analysis if composite beams are designed for vibration during design? Well, yeah, that's just using the very old-fashioned square root deflection over 18 calculation to get a natural frequency of a single beam. We're looking at whole systems here, and we're looking at not just the natural frequency of whole system, but the effect of something happening in one area to another. This is a lot more accurate, and it is all about what this publication 354 is about. It is about the accelerations that the user feels while walking and standing. It's not about the frequencies. So it's a lot more accurate, it's a newer science, and it is better. If you convert the steel beams to concrete, will it give the same results? No, it will not. The stiffnesses will be different, and you would also be working to a different publication. You'll be working to the Concrete Society publication with its recommendations. Can your analysis analyze more than one level? Absolutely, but you know, it is possible, but you know, everything is to the degree to do with sensitivity. If you were doing operating theatres for microsurgery, you probably might consider 2 or 3 stories with columns in between and continuity, and see what happens when you have a dance floor on the first floor and you on the 3rd floor are trying to do sensitive microsurgery. Absolutely, it is. You as an engineer assess what you need to know for your criteria. So ladies and gentlemen, I'm going to let that be the end of this webinar. I'd like to thank you all for coming along. We had a massive turnout today. Very, very impressed for such a specialist topic. So thank you very, very much.